Hello, welcome back to Learn Physics. In today's topic, we are going to continue with our work, energy and power. Okay, in last class we did tell our work energy theorem for a constant force. In work energy theorem for a constant force, we told that work done will be equal to final kinetic energy minus initial kinetic energy for a work done by for a constant force. For a constant force. Now we are going to consider about a variable force. In between we are changing the force, amount of force given is changing. Then if it is changing, what will be the work done? That one we are going to find out now. Okay. So first one is work done by a variable force. I am giving a force, a variable force for the moment of an object. So what will be the work done? See how we can find out the work done by an object if we are applying a variable force. Okay, so for that first we are going to draw a graph between f of x and x. At each and every position, what will be the work done? So suppose I am getting a graph like this. If I am getting a graph like this, first I will consider a small distance dx. For this small distance, work done as force is almost equal, isn't it? So I can write down work done will be equal to fx dot dx. Isn't it? This will be the work done if I am considering a small displacement dx. So that is for a small distance. Same way I can divide this whole graph into small areas. Okay, I am dividing it into small area where and all force is remaining same. See here almost same here. From here to here at a stretch if I am considering force is varying drastically, isn't it? But here if I am considering very small distance dx, the force is not changing that much, isn't it? So I can consider it as almost constant. So work done for small displacement dw, this one I am writing it as dw. Work done for a small distance dx is fx dx. Okay, so now how we can find out the total work done? Total work done if we have a small distance dx with us, work done for a small distance dx with us, how we can find out the entire portion? See, if this is the initial position and this is the final position, how I can find out? Integral xi to xf. We can integrate. If we have a small value with us, to find out a bigger value, what we should do? We should integrate. Integral xi to xf f of x dx. This will be the total work done. Or we can say from graphically how we can find out the work done? Area under the graph. Area under the graph will give you the work done. Okay, so work done we can find it out as total work done will be equal to integral xi to xf f of x dx. This is the work done for a variable force. Now, if we are getting work done, we can find out work energy theorem for a variable force. So next is work energy theorem for a variable force. Here also, first we are considering the kinetic energy. So kinetic energy is equal to half mv square. If we are applying a variable force, the kinetic energy will be changing because velocity will, if I am apply force in between, if I am changing, what will be varying? Velocity will be changing, right? So kinetic energy will be changing. dk with respect to time, kinetic energy will be changing. Half So dk by dt, change in kinetic energy, how we can find out? d by dt of half m v square. Here which is the changing quantity? Velocity is the changing quantity. So I can take half and m outside, d by dt of v square. Tell me differential of v square. Yes, d by dt of x to the power n equals, listen here, those who don't know the differentiation, d by dt of x to the power n equals n into x to the power n minus 1. Okay, so this is the formula, n minus 1. So if we are applying, this is d by dx of x to the power n. So here d by dt of v. Okay, here and here if it is same, then only we can find out using this formula. Otherwise what we should do? Half m into, what is 2v into dv by dt. This is equal to dk by dt, right? So here we can write dt and dt will get cancelled. dk equals m into, instead of v I can write it as dx by dt. Velocity is dx by dt, right? Then dv by dv. Here I can write it as m into dx into dv by dt. What is dv by dt? A. So I will get it as f is equal to ma into dx. So what will be dk? dk will be equal to f into dx. So what is the total kinetic energy? If we have a small value with us, how we will find out the total value? K equals integral xi to xf f of x dx. So here force is a changing quantity, right? With respect to distance, force is changing. So f of x dx. What is this integral xi to x of f of x dx? That is the total work done. So kinetic energy is equal to total work done. Like that we are getting. So this is how we will be proving work energy theorem for a variable force. Once more I will tell you. Here also we are finding out the kinetic energy. Okay, kinetic energy equals half mv square. So the force is changing in between, isn't it? It's a variable force. If it is a variable force, then with respect to time, velocity is changing. dk by dt we found out. d by dt, while we are finding out and cancelling everything, we will get it as m into v into dv. Instead of v, what we can substitute? dx by dt. Okay, now we are considering dv by dt. What is dv by dt? ma. m is f. ma is f, but that f is changing with respect to s. That f is a variable quantity here, isn't it? So f of x dx we are getting. So the total kinetic energy we can find out using the formula integral xi to xf f of x dx, isn't it? But here integral xi to xf f of x dx we already got it as work done. So the work energy theorem for a variable forces, total kinetic energy will be equal to integral xi to xf f of x dx, that is equal to the total work done for a variable force. Okay, so clear how we will be finding out the work energy theorem and work done for a variable force, and next is work energy theorem for the variable force. Clear? So till this time we were discussing about the kinetic energy, right? So now we are going to study about the potential energy. So kinetic energy we learned it as, kinetic energy is the energy possessed by an object due to its motion. So change in kinetic energy we got it as, it will be the work done, isn't it? So we derive the formula as half mv square minus half mu square as kinetic energy, change in kinetic energy, that is equal to the work done. Like that we proved for a constant force. If it is for a variable force, we proved it like integral xi to xf f of x dx, that will be equal to the change in kinetic energy, isn't it? Or total kinetic energy will be equal to a work done, integral xi to xf f of x dx, isn't it? So now next mechanical energy what we learned is potential energy. So what is the concept behind this potential energy? See, Earth will be attracting all the object towards it with the force of mg. Isn't it? So on the surface we will be getting a weight of mg here. So we are raising an object from the earth surface to a height h. So I am raising an object to a height h. So I am doing some work against the force of attraction. Isn't it? While earth is attracting the object downwards, I am taking the object to a particular height. So what we are doing there? We are finding out a distance. We are taking an object to a particular height. So we are doing work against the force of gravity. Okay, so we are doing work against the force of gravity. So gravitational potential energy, we can write it as gravitational potential energy will be equal to the negative work done in raising an object to a height h. So that is the gravitational potential energy, that will be equal to mgh. So f of h, if we want to find out, that will be equal to, so f of h is equal to minus d by dh of the potential energy, isn't it? V is the potential energy, so minus d by dh of v. Okay, V is the potential energy. So what we will be getting here, d by dh of mgh. V is mgh, right? So we are getting it as minus mg into dh by dh, that will be equal to minus mg. So the gravitational forces, we got it as mgh, minus mg. So that is f of h will be equal to minus dv by dh, or we can write it as f of h dh will be equal to minus dv. What is this minus dv? Initial to final, isn't it? So while we are applying dv, what is dv? It is equal to v applying initial to final value. Okay, so how we will be getting integral dv, as many times I explained, integral dv will be equal to integral v to the power 0 dv. Okay, integral v to the power 0, 0 plus 1 divided by 0 plus 1, isn't it? So that will be v. That is how we are getting v over here. Okay, vi to vf, negative sign is there, so we will get it as vi minus vf, upper limit minus lower limit with a negative sign, so we will get it as vi minus vf. So f of h dh will be equal to the change in potential energy, vi minus vf. So f of h dh, what is this f of h dh? That will be equal to the work done. So here also we are getting it as work done will be equal to the minus this change in potential energy. So here and all, what we are identifying, integral xi to xf f of x dx is dk, isn't it? Kinetic energy will be equal to, so it is ki minus kf is equal to, or kf minus ki equals w told, work done. Here vi minus vi equals work done. So from there we can identify the thing that the work done is depending only on the initial and final position. Okay, so this kinetic energy and potential energy, everything is depending on initial and final position. How it is reached to the final position, it is not at all considering, only depending on the initial and final positions. So those force which is helping to do this work, that forces are called as conservative force. Okay, it depends only on the initial and final positions. So those kind of forces are called as conservative force. It is depending only on the initial and final position. So if it is a closed curve we are considering, what will be the this energy over there or work done over there? Vi minus Vi, initial also, final also, same position. So what will be the work done in that case? It will be equal to 0. So now we are going deep into this conservative force. Okay. So in the case of kinetic energy, how we got work done will be equal to final kinetic energy minus initial kinetic energy. But in the case of potential energy, work done will be equal to Vi minus Vf. Isn't it? So work done is depending only on the final and initial point. So depends on end points. Okay, and it is derived from a scalar quantity. So it is derived from scalar quantity. So it is that kind of forces are derived from a scalar quantity. And if it is a closed curve, closed one, that is initial and final points are same. If it is closed one, initial and final points are, that is initial and final points are same. If initial and final points are same, then the work done will be equal to 0 there, isn't it? Initial and final positions are same, then the work done will be equal to 0. So such kind of forces are called as conservative force. Conservative force. So conservative force is the work done by the force only if it is a closed curve, it will be equal to 0. It depends only on end points and derived from its a scalar quantity. Okay, so here we can write down it as, see, both are work done, isn't it? So I can write it as Kf minus Ki will be equal to Vi minus Vf. So minus Vf I am taking to the left side. So Kf plus Vf, that will be equal to this negative sign I am taking to the right side. So it will become Vi plus Ki. So what is this? Final kinetic energy plus final potential energy. So total energy, final total energy will be equal to initial total energy. So this is called a conservation of energy. What is conservation of energy? Energy can neither be created nor be destroyed, but the total energy remains constant, isn't it? Final energy will be equal to conservation of energy. So these are the conservation of energy. Okay, clear? So these are the important topic which we are learned today. In that, very important one is work energy theorem for a variable force and work done by a variable force. Okay, so clear all of you? So I hope all of you understood all those things. If you like the channel, please don't forget to subscribe. Thank you for watching. Bye.